Hi, my name is Harlan. Welcome to the H Matchakbon Mechanical Engineering channel. Our topic for this video tutorial is the psychrometric chart and air conditioning processes. A psychrometric chart is a graph of the thermodynamic properties of moist air at constant pressure. Major lines and scales on the chart are follows: dry bulb temperature lines, which are these lines here. Okay, the vertical lines. These are the dry bulb temperature lines, and we have the wet bulb temperature lines here. This is the wet bulb temperature lines, and then we also have the enthalpy or total heat lines. This one here is the enthalpy or total heat. And also we have relative humidity lines. This one here is curve, RH. Okay, this is for 40% RH here. And this one is 20% RH. And we have the humidity ratio or moisture content lines, which are these here shown. Humidity ratio. And we also have the saturation temperature or dew point scale. We have this one here. Saturation temperature and dew point scale. These are the dew point temperatures. And we have your specific volume lines shown here, these lines. We have 13.5 cubic feet per pound of dry air. This one is 13.0. This one is 14. This one is 14.5, this line here. Okay, so the chart includes a protractor nomograph showing two scales. The first one is enthalpy humidity ratio scale, and the second one is a sensible heat ratio scale. I will show you here. Okay, so this is the protractor, and this one is a sensible heat ratio, and this one is the enthalpy humidity ratio scale. So process lines are the lines drawn on the chart showing the changes in psychrometric conditions. So the protractor nomograph is used to establish the slope of a process line. Relative humidity is the ratio of the amount of moisture in the air to the maximum amount of moisture that the air can hold at the same temperature and pressure. Saturation is a condition wherein air is no longer able to hold any more moisture at the given temperature. So for example, we have 86 Fahrenheit dry bulb and 70 Fahrenheit wet bulb outside design condition during summer. We determine, number one, the moisture content, the total heat, the relative humidity, the specific volume, and the dew point. So here, shown in the chart, you have the dry bulb here, a temperature, and this one will be your wet bulb temperature here. So the wet bulb is 70, and the dry bulb is 86, right? So you are going to determine the moisture content. So you can find here the moisture content. So the result will be 0.012 pounds of moisture per pound dry air, and the total heat will be 34 here. So this is 34 BTU per pound of dry air total heat. And the next requirement will be the relative humidity, We find it in here. So the relative humidity is 45%, okay, or you can also use 0.012 divided by 0.0265, which is 0.45, okay. And you have here the specific volume, 14.01 here. Specific volume, 14.0, is 14.0 pounds cubic feet per pound of dry air. So this one is 14.01. And the next requirement will be the dew point. And the dew point here is 62.5. The dew point is at point number 2, which is 62.5. And another example, for a 75-degree Fahrenheit dry bulb and a relative humidity of 50% RH, the design condition during summer determine the moisture content, the total heat, the specific volume, and the dew point. So we will draw here 75 dry bulb and at 50% RH. So 75 dry bulb, 50% RH, and you can find the moisture content here. Here you can read it from here. So the result will be 0.0095 pounds of moisture per pound dry air, and the total heat will be 28.2 here. You can find the total heat here. So it's 28.2 BTU per pound of dry air, and the specific volume will be 13.7. This one is 13.5 here. So this one is 13.7. And the dew point is 55. So it's 50 here, 60. So this one will be 55. That will be the dew point temperature. So in this case, like say you have a given point O, you have a total heat of 34 BTU per pound of dry air, and it has two heat components, the sensible heat and the latent heat. So this scale here, from this point here going up, this one will be your sensible heat, and this one will be your latent heat. So this will be the two components, and the sum of the sensible heat and the latent heat will be the total heat, or the enthalpy in BTU per pound of dry air. The process is plotted on psychrometric chart. So for example, you have an air mixing process. You have outside here air here at point 1 with this following data: at dry bulb temperature 86 Fahrenheit, wet bulb temperature 70 Fahrenheit, and the return air point 2 at dry bulb temperature 75 Fahrenheit and 50% relative humidity is being mixed until to point 3, which is the mixed air, before it goes into the filter and the cooling coil and the heating coil. So if we plot this one, okay, how to calculate the mixed air dry bulb temperature, the fixed quantity, for example, a fixed quantity of 1/4 of outside air and 3/4 of return air as mixed. So you know that the outside air is 86 Fahrenheit dry bulb and 70 Fahrenheit wet bulb, and the return air is 75 Fahrenheit dry bulb and relative humidity of 50% RH. We find the mixed air conditions. So we calculate the mixed air dry bulb temperature as follows: 3/4 times 75 plus 1/4 times 86. The result will be 77.5 degrees Fahrenheit. So we can show this here. Okay, the point 1 and point 2 is mixed until it reaches point 3. So we have calculated it as 77.75 Fahrenheit. Okay, and so we can determine the properties here. So of this point from your psychrometric chart, we can determine the moisture at 0.010. We can determine the wet bulb temperature. We can determine the RH. Okay, and we can also determine the enthalpy in BTU per pound of dry air. So here, the moisture content was 0.010. The total heat is 30, shown here. Total heat is 30 BTU per pound of dry air. And the specific volume is 13.75. Okay, specific volume is between 13.5 and 14. So it's about 13.75. And you have your dew point here, and the dew point here will be 57.5 degrees Fahrenheit. This one here. Okay, 57.5. So let's now take up air heating process. We have already done with the mixing process. We now take up air heating process. So for example, we have air at 0.3 having 50 Fahrenheit and 40 degrees RH will be heated until it reaches 0.4, and the target amount of the target dry bulb temperature will be 70 Fahrenheit. So, and we will graph this here later after solving. Mixed air at 50 Fahrenheit, dry bulb and relative humidity of 40% RH is heated using a steam coil to a temperature of 70 Fahrenheit. Determine the heat added. The heating process adds sensible heat to the system. Take note that the steam does not come in contact with the air here. It is just inside the coil. So it's just the heat is being added to the air. So we can graph it here from 0.3 at 50 Fahrenheit dry bulb, 40% RH is being heated to 70 Fahrenheit dry bulb. Okay, and we determine the heat added. So at this point, at 0.3, the total heat will be this amount. So this is a little more than 15. So that's why you have 15.5 in here, and this one here at 0.4 will be equal to 20.5. So 20.5 minus 15.5 is 5 BTU per pound of dry air will be the heat added to the system. Okay. So let us now discuss air cooling process. So for instance, you have air at 0.3 having a dry bulb temperature of 85 Fahrenheit and humidity of 40% RH. It needs to be cooled down to 65 Fahrenheit at 0.4 here. So we find the amount of air, the heat that needs to be removed from the system. So mixed air at 85% degrees Fahrenheit dry bulb and relative humidity of 40% is cooled to a temperature of 65 Fahrenheit. Determine the heat removed. So the heat removed is the heat at 0.3 minus the heat at total heat at 0.4. So we can see in the graph here, 0.3, your heat will be 30, 31, 32, 32.3, and at 0.4 it will be 27. So you subtract, take the difference between the two, so you have 32.3 minus 27, we have a heat removed of 5.3 BTU per pound of dry air. So let's go now to air humidifying process. You have here air at 0.3 with a temperature of 35 Fahrenheit, 70% RH is being heated to 0.4, wherein the dry bulb temperature desired is 72 Fahrenheit. And let us see first from this what happens in the chart. Okay, because our intention is to maintain the temperature of 72 Fahrenheit, but we wanted a relative humidity of 50% in at 0.5. So determine the relative humidity at 0.4. That's the first question. And find out how much moisture has to be added if the room dimensions are 30 by 30, ceiling height is 8 feet, with 2 air changes per hour, so that 50% relative humidity can be achieved. So let us go now to the graph. You have a 35 Fahrenheit, 70% RH at 0.3 here, and it's being heated up to the temperature of 72 here, Fahrenheit dry bulb. So the resulting RH or the resulting RH here will be very low. It's in fact less than 20%. So it is not comfortable because the air is too dry. The moisture is only 0.003 pounds of moisture per pound of dry air. So what needs to be done here? We need to add moisture here. So we will add moisture. Okay. Now, so here, so 19% relative humidity at 0.4. The volume of the room, it's 30 by 30 by 8 feet. So we have 7,200 cubic feet. For 2 air changes per hour, the ventilation air will be 7,200 cubic feet times 2 per hour. So we'll have 14,400 cubic feet per hour. And the outside air at 35 Fahrenheit, dry bulb and relative humidity of 70% RH has a specific volume of 12.55 here. Specific volume is 12.55. Okay. So the outside air at the same 35 Fahrenheit dry bulb and relative humidity of 70% RH has a density of 0.08 pounds of dry air per cubic foot. It is the reciprocal of your specific volume. And the quantity of outside air now will be equal to 0.08 pounds per dry air per cubic feet times 14,400 cubic feet per hour. We have 1,152 pounds of dry air per hour. So the chart indicates that the moisture needs to be increased. You can see from your chart here, we want a 50% RH, so we need to have a moisture of 0.009 pounds of moisture per pound of dry air. So the increase will be 0.009 minus 0.002 for 0.003 rather per pounds of moisture per pound of dry air. So we have 0.006, okay, pounds of moisture per pound dry air will be the increase of moisture that will be needed. So multiply this value by the amount of dry air per hour, 1,152, and the result will be 6.9 pounds of moisture per hour. And this value is equivalent to 0.827 gallons per hour. If you convert the pounds into gallons, pounds of water into gallons. So let's go to the steam jet humidifier, a very popular type of humidifier. So again, from the same setup, 35 Fahrenheit, 70 Fahrenheit, 70% RH at 0.3, and will be heated to 0.4 to attain 72 Fahrenheit dry bulb. And we need to have at 0.5 here, 50% RH. What are we going to do? The outside air at 35 Fahrenheit dry bulb at relative humidity of 70 is raised to a temperature of 72 Fahrenheit, and then saturated steam at 212 Fahrenheit is sprayed into the heated air to achieve 50% humidity. Question number 1, determine the relative humidity at 0.4. And number 2, find out how much steam has to be added if the room dimensions are the same, 30 by 30 by 8 feet with 8 air changes per hour. So, solution. Steam enters the humidifier and is sprayed into the airstream. The total heat needed to prepare the saturated steam at 212 Fahrenheit consists of the heat needed to raise temperature of water from 32 Fahrenheit to 212 Fahrenheit. So it's 180 BTU per pound. Plus, you need to add the heat needed to vaporize the water at 212 Fahrenheit into steam at the same temperature of 212 Fahrenheit. So it's 970 BTU per pound. So the total will be 1,150 BTU per pound. So similar to the previous example, the relative humidity at 0.4 is 19% RH. And the volume of the room is 7,200 cubic feet for 2 air changes per hour. The ventilation air will be 14,400 cubic feet per hour. So we locate 1,150 BTU per pound on the lower scale of the protractor neurograph and connect to the center of the protractor. Then we create a parallel line initiated from 0.4 until 50% RH line is reached. This will be 0.5. I will show you. So we locate 1150 here, BTU per pound of dry air, connect to the center of the protractor, and draw a parallel line, parallel to this one, starting from 0.4. So we have here this blue line here, yeah, until we reach 50% RH. So this will be now your 0.5. So you can see you can read out the moisture content that is required here, and you subtract it from your initial moisture here. And you also have, take note here, you will have your sensible heat, and then you will also have this one here. Okay, from here to here will be sensible, and from here to here will be latent heat. Okay. So the steam raised the temperature from 72 Fahrenheit to 74 Fahrenheit. Take note, 72, 74.5. And the total heat added by the steam humidifier is 27.5 minus 20.5. 27.5 minus 20.5 here at 0.4. So the total heat will be 7 BTU per pound of dry air. The latent heat added by the steam humidifier is 27.5 minus 21. Yeah, this one here is 21. So 27.5 minus 21 represents the latent heat added. So the actual moisture added by this steam humidifier is equal to 0.009 minus 0.003. So 0.009 here minus 0.003. And you can calculate the actual moisture added by the steam humidifier as 0.006 pounds per pound of dry air. And specific volume of the entering air at point B is 13.45 cubic feet per pound of dry air. Let's see here, 13.45 entering air, 13.45. Okay, the specific volume entering air. So 13.45. So from that, the volume of the airflow is 14,400 cubic feet per hour, and the weight of the air will be 14,400 cubic feet per hour divided by 13.45 cubic feet per pound of dry air will be 1070.6 pounds of dry air per hour. And the weight of the moisture added will be 0.006 pounds per pound of dry air times 1070.6 pounds of dry air per hour. We will have 6.42 pounds of moisture per hour. And since water weighs 8.34 pounds per gallon, the moisture added will be 6.42 divided by 8.32 pounds per gallon. You will have 0.77 gallons per hour. The steam humidifier adds 7 BTU per pound of dry air. The total heat added is 7 BTU per pound of dry air times 1070.6 pounds of dry air per hour. You will have a total of 7,494.2 BTU per hour. So let us discuss now air washers. Air washers are also used as humidifiers when added moisture is required and not too much heat, is as in locations of warm climates. Air washers can either be circulating or they can be heated air washers. So let us tackle first the recirculating air washers. So you have a supply air fan here, the airflow, and from 3 to 4, the only change will be the air is subjected to air washer, and the water is being circulated with a pump from the sump and goes back to the air washer here, sprayed into the air and settles down on the sump and is being circulated. So sensible heat is changed to latent heat to vaporize the water. Hence, the dry bulb temperature of the air is reduced. The wet bulb temperature of the air is the same as the water temperature because the water is circulated. The total heat remains the same. That is why the process is called adiabatic. The process line follows the constant enthalpy line on the chart. So from 3 to 4 here, at given 30% humidity and 85 Fahrenheit, and it's subjected to an air washer so that you can attain 50% RH, and it's recirculating. And so it will be the process between this one, constant enthalpy, it's adiabatic here. So it will be somewhere here. Okay? And 50% humidity is your aim. So you will have a temperature between 75 and 80 Fahrenheit. So let's now go to the heated air washer. So actually, it's more or less the same construction, except you have a heat exchanger here, where you have a hot water supply and hot water return here to heat up the water when it goes to air washer in your sump. So supposing that air at 70 Fahrenheit and 30 RH is sprayed with water that is heated to 80 Fahrenheit, what happens? The temperature of the water will always be on the saturation curve. Number two, the resulting dry bulb temperature of the air will settle between 70 Fahrenheit and 80 Fahrenheit, in this case 0.6. Let's look at this closely. So we have here 0.3 at 70 Fahrenheit, dry bulb and 30% RH with a given moisture of 0.00 5 here pounds of moisture per pound of dry air, and it's being heated to it's being sprayed here until it reaches 0.4. Okay, so the temperature of the water will always be in the saturation curve, like here. And the resulting dry bulb temperature of the air will settle between 70 and 80, in this case 0.6. The resulting temperature, okay, will be 0.6. So you will have an increase in humidity here. Okay, see, the moisture content is now 0.016. And as the humidity demand reduces, the water temperature goes down the saturation curve as it surrenders heat to the air. The resulting dry bulb temperature of the air settles at 0.7. So here, so as the demand for humidity reduces, so the temperature here is lower, and so it will settle at this, the air temperature will settle at 0.7, and you will also have lesser humidity, lesser moisture per pound of dry air. Okay? So supposing that the 80% dry bulb and 80 degrees Fahrenheit dry bulb and 80 degrees Fahrenheit wet bulb is sprayed with water that is heated to 75. What happens? Air is being humidified, but at the same time cooled a little bit. So in our previous example, we have here, see, from 80 to 75, the temperature of the water. Okay. So it's cooled a little bit. Okay. 80 and 60 here. It's cooled a little bit. Sorry. Here, 80 and 60. Okay. And okay, this one will be 60 Fahrenheit wet bulb. That's approximately 30% RH. And we will cool it down to 75. So what happens, see here, the temperature of the water will always be in the saturation line. And so it's about, like say, it's 75. So the resulting temperature will be between this temperature and this temperature here, 75. So it will be cooled a little bit to about 76. Okay, roughly. Yeah. and air is humidified also at the same time. Okay, so you add humidity and cooled it a little bit. The resulting dry bulb temperature of the air will settle at 0.6, as I have shown. Okay, I've shown to you. Again, the humidity demand reduces, the water temperature goes down, the saturating curve, and surrenders heat to the air, and the resulting dry bulb temperature will settle at 0.7. So if the humidity demand is lower, so the temperature of the water will be at 70, and so it will settle at 0.7. So it's you have a lesser humidity than 0.6, but it's also cooler. It's also cooler here, lower dry bulb temperature at 0.7. So now let's take up cooling and dehumidification. Supposing you have air here at 0.3 with 85 degrees Fahrenheit dry bulb and 60% RH, and you need to cool it down, and you have a cooling coil here at 4, and we desire at 0.5 a dry bulb temperature of 65 Fahrenheit. So what happens? Cooling and dehumidification can be accomplished in a single process, and it involves both sensible and latent heat cooling. When surface temperature of the coil is lower than the dew point, take note, of the entering air, moisture is removed from the air. If the so you cannot remove moisture unless the temperature of the coil is lower than the dew point of the entering air. So we will give you an example. Air entering at the cooling coil at 85 degrees Fahrenheit, dry bulb, and 60% relative humidity. The moisture of the entering air is 0.016 pounds per pound of dry air. The chart shows a dew point temperature of 70. Okay, so it shows here at 0.3, showing a dew point temperature of 70. See? So dry bulb temperature 85, 60% RH. You can see the dew point at 70 Fahrenheit and moisture of 0.016. And you desire something like at 0.5, air at 0.5. So, and then at 0.4, the coil temperature is at lower, which is given here to be 60 or 55 Fahrenheit, okay, which is lower than 70. If you don't have a temperature lower than 70, you cannot remove moisture from the air. So it has to be lower than this. So say, for example, you have 55 here. So see, okay, in order to remove moisture from the air, it has to be cooled to a temperature lower than that of its dew point. Supposing the coil will have a surface temperature of 55 Fahrenheit, and since the coil is not 100% efficient, take note, air leaving temperature will probably be at 65 Fahrenheit dry bulb and 62 Fahrenheit wet bulb. And this can be confirmed by measuring the actual dry bulb and wet bulb temperatures using a sling psychrometer. And the moisture content of the leaving air will be 0.0115 pounds per pound of dry air. So this condition can be confirmed by measuring the air at 0.5, air leaving the coil at using a sling psychrometer. So I measure the dry bulb and the wet bulb, and you can determine this point. Okay. So the solution, the specific volume of the entering air is 14.1 cubic foot per pound of dry air. Okay, here, 14.1 cubic foot per pound. And the amount of moisture removed is 0.016 minus 0.0115. The result will be 0.0045 pounds per pound of dry air. So this one will be the amount of moisture removed from 0.3, the moisture at 0.3 minus the moisture at 0.5. If 4,000 cubic feet per minute passes through the coil, the weight of the air will be 4,000 cubic feet per minute times divided by 14.1 cubic foot per pound of dry air will be 283.69 pounds of dry air per minute. And the weight of the moisture removed will be 0.0045 pounds per pound of dry air times 283.69 pounds of dry air per minute. The result will be 1.28 pounds per minute, or 76.6 pounds of dry air, pounds of moisture per hour. Since the water weighs 8.34 pounds per gallon, the moisture removed here can be calculated by dividing 76.6 pounds of moisture per hour divided by 8.34 pounds of water per gallon, and the result will be 9.18 gallons per hour. That will be the amount of moisture removed. So we can also use air washers for the humidification. How do we do it? Supposing again, we have 85 degrees Fahrenheit here and 50% RH at 0.3. And you have here for your air washer, you spray chilled water supply at 50 degrees Fahrenheit. The temperature of the chilled water supply here sprayed, and then and the water at the sump will be returned to the chiller, and you have to determine condition number 5. So the air entering is 85 dry bulb and 50% RH, which is 0.3. The moisture of the air entering is 0.013 pounds per pound of dry air here. Okay, so 0.013. This is 0.3 here. And okay, the temperature of the chilled water being sprayed is 50 Fahrenheit. 50 Fahrenheit, this one, this temperature here at the saturation line. Air that comes in contact with the spray droplets follows the saturation curve to the spray temperature of 50 Fahrenheit of 0.4, and then this will mix with the air that did not come in contact with the droplets. Here. The resulting air mixture will be at 0.5. This can be determined again using this ring psychrometer by measuring the dry bulb and the wet bulb temperatures of the leaving air. So we can plot out 0.5 here. Supposing 0.5 is measured at 60 Fahrenheit dry bulb and 50 degrees wet bulb, the moisture of the leaving air will be 0.009 pounds per pound of dry air. See here. Okay. So the amount of moisture removed is 0.013 minus 0.009 will be equal to 0.004 pounds of moisture per pound of dry air. And again, supposing 4,000 cubic feet per minute passes through the coil, the weight of the air will be 4,000 cubic feet per minute divided by 14.03 cubic feet per pound of dry air, the result will be 285.1 pounds of dry air per minute. And so the weight of the moisture removed is 0.004 times 285.1 pounds of dry air per minute. The result will be 1.14 pounds of moisture per minute, or 68.42 pounds per hour. So where did you get 14? You have a 14.03 here. It's 13.5. This is 14. Okay, so this one is 14.03 cubic feet per pound of dry air. So that's how we got that value. And since water weighs 8.34 pounds per gallon, the moisture removed is equal to 68.42 pounds of moisture per hour divided by 8.34 pounds per gallon. The result will be 8.2 gallons per hour. Now let us go to the humidification and reheat. Again, we have here an entering air at 85 Fahrenheit, dry bulb at 50% RH. You subject it, you pass it through the cooling coil, and the result as based on your dry bulb 4 and wet bulb 4 will be dry bulb 55 Fahrenheit, 54 Fahrenheit, supposing as measured, and since here, if you graph it, the humidity is so low now, slow now, but the temperature is very low. It's not comfortable. So we wanted to raise the temperature. Okay, we have already an acceptable amount of moisture here, but we want to raise the temperature to a comfortable level of 70 Fahrenheit at 0.5. Yeah, so what we will do here, we will subject it to heating coil or a reheat until we reach 70 Fahrenheit. So this one will be the graph from 0.3. It will go as much as closer to the saturation line and to the temperature at 0.4, closer to the coil temperature. And we have measured it at 55 and 54, 55 dry bulb, 54 wet bulb. And so we need to reheat it. After removing some moisture in it, we reheat it to 70 Fahrenheit dry bulb, so we will reach 0.5. So it will just be a horizontal line here. So this will be, you can now read up the properties of air at 0.5. So we have already discussed the processes involving the psychrometric chart, the air conditioning processes, and I would like to invite you and your friends to watch our video tutorials at H. Machicon Mechanical Engineering channel on YouTube. There are more video tutorials coming our way. Thank you. Bye now.